Let's move on to section 8.2, which we've been talking about integers, and we discussed addition and subtraction. So we want to talk about multiplication and division as well. Okay, so for multiplication, we can use some similar explanations that we have seen before. So for instance, we can still think of multiplication as repeated addition. It just, when it referencing negative numbers, it looks a little bit different. So I might instead say, if I'm looking at 3 times -4, what I'm doing is I'm adding -4 to itself 3 times, and I see that I get -12. We can also explain or try to understand multiplication through examining patterns, just like we did with subtraction. So if I already know multiplication on the whole numbers, so just starting off with some basic examples there. If I look at 3 times 4, that's 12, and then 3 times 3 is 9, and 3 times 2 is 6, and 3 times 1 is 3. And I see that each time I lower the number, I'm just dividing by 3, right? Each time I lower the integer that I'm dividing by, multiplying by. And we know, so 3 times 0, I'm sorry, I'm not dividing by 3. I'm subtracting 3, right? That's what I'm doing here. There we go. So each time I lower the number, I'm subtracting 3, so we expect 3 times 0 to be 0, which we know is true, and 3 times -1 to be -3, and 3 times -2 to be -6. This pattern just continues over and over. And the same thing goes if I were to start with a negative number, like I follow this pattern, I know that -3 times 3 is -9, and -3 times 2 is -6. Again, I'm just going to keep subtracting 3 to follow this pattern. So -3 times, oh my goodness. Let's rewind. Okay, so here I am starting with -3, and we'll say from this pattern, I figured out that 3 times -3 is not -9, and -3 times 2 is -6. And so we see from this pattern, each time I'm increasing each time I'm decreasing the number I'm multiplying by, here I'm adding 3. All right, so when I multiply by 0, I should get 0. When I multiply by -1, I should get 3. And when I multiply by -2, I should get 6. And when I multiply by -3, I should get 9, and this should continue forever. Okay, so examining these patterns should tell us what to expect when we multiply by negative numbers, right? Because we already know what happens with whole numbers. And finally, of course, we can use our set model. So here's the set model representation. We just took the number -3, which looks like just this set with 3 red dots in it. And then to multiply it by 4, I'm just going to replicate that set 3 times. And I see all in all, I'm left with -12 because I have 12 red dots altogether. Great. So again, my definition is extended from whole number addition, multiplication. So again, basically we take what we know about the whole numbers and we just extend it in this case-by-case basis. It's kind of a silly way to do things. There's a reason we could talk about it, but I think it's not that important. So We won't. But what is important are these properties that we have for multiplication under the, or sorry, for the integers under multiplication. Sorry, I don't know why this bubble is not going away. I'm trying to, hoping it will go away. There it is. Okay. Okay, so we still have, if we're looking at the integers, they're still closed under multiplication, right? If I multiply two negative numbers, I get a positive number, but that's fine. They're still integers. If I multiply a positive times a negative, it's going to be negative. Still count the integers, right? So this set is still closed under multiplication. It's still commutative as we would expect. It's still associative as we would expect. There is still an identity, a multiplicative identity. There was one for the whole numbers. It did not go away, right? It's still distributive over addition. If any of these words are not ringing a bell, go ahead and I think that these properties are explicitly stated out in the section, but they're also, of course, in the notes and in the section from previous sections because we've talked about them many times. What is new, though, is multiplicative cancellation, I believe. And multiplicative cancellation says that if I have three integers, and we'll say that this c is not 0, and we say that if AC equals BC, then we can basically, this is telling me, hey, it's okay to divide by C on both sides and get that A is equal to B. So again, these things might seem a little silly, but this is what is allowing us to solve equations. So these properties make that possible and are what allow us to solve equations. And again, I think it does seem silly when you're like, okay, well, great, but I already knew that. But I think it helps point out when we have these basic properties, I think it helps emphasize properties that we do not have in ways that it is not okay to solve equations. So for instance, we can divide both sides by C, but I can't say divide one side by C and one side by some other number at the same time, right? So I think pointing out some of the properties that we do have is helpful for kind of emphasizing the ones that we don't. What is new is we haven't really been able to talk about zero divisors because we've been pretty wishy-washy as to whether or not the whole numbers contain 0, which, you know, eventually I'll stop griping about that with this book, but not today. So now for sure the integers contain 0. So what is a zero divisor? So this is also a really important property when it comes to talking about solving algebraic equations. And I think students don't really see it until that point, and it's kind of a shame because this does kind of trip people up quite a bit. So if I have two integers, A and B, and I know that they multiply to be 0, I know that either one or both of them has to be 0. Basically what that's saying is if I multiply two things, I know, and I get 0, I know it's not going to be the case that one was 2 and one was 3. I have to have one of them be 0. There's no other way. And so this shows up, it rears its ugly head all the time when we solve algebraic equations. So even just something as simple as, say you factored a polynomial and you get x plus 3 times x minus 1 is equal to 0. What you then usually do is you say, hey, that means either x plus 3 equals 0 or x minus 1 equals 0, or both. That's fine too. So that means x equals a negative 3 or x equals 1, right? This is our normal process. But notice we could not do that if this thing were not set equal to 0. And this is what trips up so many students, is they'll say, hey, let's isolate everything, get all the variables on one side, be able to factor, but maybe they'll have a 1 over here or a 7. I cannot use this property at all because just because two things multiply to be 7 doesn't mean that either one of them is 7. Well, okay, 7's prime, so that's a weird example. But just because two things multiply to be 6, say, it doesn't mean that either one of them is 6, right? It could be that they're 2 and 3. So here, this is one of those things we tend to basically completely ignore until students are thrust into algebra, and then this becomes extremely difficult and confusing because this is something they don't have a word for, and so they haven't been able to differentiate this property for zero divisors versus other numbers. So I find this property very interesting and important. Okay, so a couple other little theorems. Again, pretty, they maybe symbols are not things you've seen in this formulation before, but pretty intuitive. So theorem 1 says if I multiply an integer by a negative number or by a -1, I just get the opposite of that integer. Okay, no one's surprised there, hopefully. Theorem 2 says basically if I take -a times b, that is the same thing as negating the whole product. So you might, if you want to see an example for something like this, what this says is hopefully something that's very clear to you once you see it as an example. But if it says something like this, if I take -2 times 3, that's the same thing as saying -2 times 3, which is -6. Okay, so hopefully you knew this, right? This is how we work with multiplication of negative numbers. And theorem 3 basically says if we have -a times -b, that's the same thing as a times b. So again, I encourage you, if these things seem unintuitive to you, to just plug in a couple integers to make sure that that makes sense. Okay, touching on division very quickly. We know that if we have two integers a and b, we basically define division again to be the unique number that I multiply b by to get a. So a divided by b is really the number c that I multiply b by to get a. This is not a new definition. It's a silly seeming formulation. We're just defining division in terms of multiplication. Nothing new, sounding maybe more complicated than it needs to be. All right. Now we're finally going to talk about something that is that we haven't had much opportunity to discuss, and that is negative exponents. So again, a nice way to explore negative exponents, and as we've kind of seen this as following the pattern from this section, when we introduce negative numbers, a nice way to introduce negative numbers is by looking at patterns. I got real meta. Okay, so for instance, I know what a cubed looks like. It looks like a times a times a. So let's examine kind of what happens when I go down and I look at a squared, right? So that's a times a. And notice what I'm doing each time is I'm dividing by a factor of a. And I know that a to the 0 is 1 as long as a is not 0. So we're assuming that. Let's put a is not 0 for good measure, because 0 to the 0 is undefined, as we've discussed. And so what I expect is when I raise a to the -1, the pattern is going to continue. I'm going to divide by a, and so this should be 1 over a. And I'm going to divide by a again in the next step, and this should be 1 over a squared, and I'll divide by a third time and get 1 over a cubed, right? And we can continue this pattern all day. And so that's actually what these negative exponents are. Great, that is how we define them. A to the -n is just 1 over a to the n. Great, so I'll look at a couple of examples, and then I want to talk about this little note I have off to the right here, but I'll talk about these first to make sure that this is making some sort of contextual sense here. Okay, so 7 to the -2, that's really just 1 over 7 squared, which is 1 over 49. Just to give some kind of context for what these things look like and how they work. Okay, 3 to the -10 is just 1 over 3 to the 10. Of course, I could take 3 to the 10th power and write this as a nicer fraction. I'm not going to do that because that's way too big of a number, but this is just to help us get an idea of what these things look like. Okay, 4 to the -3, or sorry, 1 over 4 to the -3 then is equal to 1 over 4 cubed, right? And so to understand what this looks like is, so we're dividing by a fraction, right? And we know how to deal with that. So let's rewrite what's happening. We're taking 1 and we're dividing it by this fraction 1 over 4 cubed. So that's the same thing as taking 1 and multiplying by the reciprocal, which is 4 cubed over 1, or just 4 cubed. Right? So it's 1 times 4 cubed, or just 4 cubed. Great. Okay, which if we wanted to write, we could write is 64. But the point here is to kind of notice this pattern that really this negative exponent is telling us to either kind of move up or down this. Yeah, the negative is kind of telling us whether to move up or down the 4 cubed. So here, 4 to the negative 3 is the same thing, or say 1 over 4 to the negative 3 is the same thing as 4 cubed. And 3 to the negative 10 is 1 over 3 to the 10th. So basically it's telling you if it's in the bottom, move it to the top and make it positive, or if it's in the top, move it to the bottom and make it positive. If that makes sense. If it doesn't make sense, what I just said, you can always just write it in these kind of drawn out ways, and that's absolutely fine. Of course, I should say, we talked about, in the last chapter, we talked about scientific notation. Scientific notation we talked about as being really useful for writing very large numbers. It's also really useful for writing really small numbers because we can think of 10 to the negative 5th is really just 1 over 10 to the 5th. So I'm dividing 9.61 by 10 to the 5th, right? So I'm dividing it by this very large number. And so what this is I'm moving my decimal 5 places to the left. So that means I should have 1, 2, 3, 4 zeros in front because I just took this decimal that was here and I'm moving it 4 places to the left. Okay. So that number is not too difficult to write, but you can imagine if I have like a lot more zeros in here, using this scientific notation is really helpful for writing these very, very small numbers. Last little example here illuminates we can use all the other same rules for exponents that we had before with positive exponents, and they work basically the same with negative exponents. So here, if I wanted to simplify this expression of 6 cubed over 6 to the negative 7th, I can just use the fact that this is just 6 cubed, and I'm going to move that 6 to the negative 7 to the top by making it 6 to the 7th. And now I have the same base, which is 6. So to combine these exponents, I take the base, oops, I don't know why it does that so much. I take the base and I add the exponents to be 10. So this is 6 to the 10th, which of course I could compute, but seems like not the point. Okay, great. So one last little comment on exponents is to be very careful about, here we've been talking about negative exponents, but also be very careful about negative bases. So be very careful about, in particular, this difference between negative 2 to the n in parentheses and negative 2 to the n with no parentheses. What this one means is take negative 2 and multiply it by itself n times. So notice this number could be negative or it could be positive, right? If n were 2, that would just be negative 2 times negative 2, that's positive 4. This one says the negative is implied to be out front, and the only thing we're taking to the nth power is 2. So it's negative 2 times 2 n times. So this is definitely a negative number. There's no changing. So if the parentheses are there, it's telling you to raise the to include the negative. If they're not there, the negative we can imagine is out front. So it's like saying -1 times 2 to the n. Okay, so just a comment about notation there, and that's really just a notational convention. It could have gone either way. Okay, great. And last but not least, we did talk about ordering with the whole numbers, and in fact with with fractions. We can still, of course, order with the integers. Remember this symbol, A with the caret B in this direction, says A is less than B. And the properties, it's still transitive. I'm still able to, if I add the same value on both sides, it does not change the inequality. But what does happen now is when I talk about multiplication, it depends on whether I'm multiplying by a negative or a positive integer. So let's say I start with A is less than B, and I multiply both sides by a positive integer, then the inequality is preserved in the same direction. But if I start with A less than B, and I multiply on both sides by, say, a negative number, that's what this means. This means n is negative, right? It's less than 0. Then I have to flip the order of the sign. So I'm sure this should be jogging your memory, but I just wanted to call that to attention here. Okay, so again, these last two little examples are just calling on the reference I made before about signs. This kind of, again, references this issue of just because I say -a does not mean I'm talking about a negative number, and I believe that that is the issue with both of these problems. So these are ones you might want to take a look at and chat with me about if you would like. And next time we'll be moving on to chapter 9 to talk about, to extend our the numbers that we're talking about to talk about rational and real numbers. Okay.